We hear about probabilities every day. 20% chance of rain, the odds on a lottery, risk of a side effect. And behind those numbers is a simple question. How uncertain are we? Probability is a mathematical way to make predictions in an uncertain world, from weather forecasts to reinforcement learning in AI. So let's build this theory from the ground up. Hey, I'm Oliver. I study computer science and I make quick, accessible explainers for maths and computer science concepts. Today we're diving into probability theory, the framework behind weather forecasts, insurance risk, and even AI systems that detect cancer from images. As I've briefly mentioned, the simple question behind probability is how uncertain are we? To quantify how uncertain we are for an outcome to occur, we need to know what all our outcomes are. In probability theory, this would be called the sample space. For the example of rolling a 6-sided die, our sample space would look like this, all numbers from 1 to 6. These are all possible outcomes that rolling die can yield. We can get a 1 on top, 2, 3, 4, 5, or 6. Once we've defined all possible outcomes, we need to define the set of outcomes which we care about. And this is also called an event. And an event E is just a subset of our sample space, meaning that we only care about certain entries here. For example, our event can be 2, 4, and 6. So rolling an even number. Now, probabilities help us then assign what the likelihood is of such an event to occur. And that always given the sample space it is defined over. So the event of an even number occurring, or 2, 4, and 6, is dependent on what all our possible outcomes are. Since if we just have a die which only has even numbers, then the probability is different than if we have all numbers. To formalize probabilities, we use something called random variables. In this case, we call our random variable x. And a random variable takes each outcome in the sample space and assigns it a probability we can work with. In our case, with rolling a die, our random variable would take the value showing on the die, so the number that's on top. And this then helps us link outcomes and numbers to give us a numerical description of outcomes. So this allows us then to interpret x equals to 1 as meaning the number that is showing on the die is 1. Using this, we can then define what the probability is of this event occurring. We write this with this p, and then inside brackets, what our random variable is equal to. So if we write p of x equals 1, this tells us what is the probability of x equaling to 1, so the number 1 showing on the die. In our case, this would be 1/6, assuming we have a fair die. So, on average, when rolling a die, we will get the value 1/6 of the time. Now, depending on the sample space and the exact scenario you are working with, these probabilities can be different. For example, if we have a not fair die, so one that might have a weight on one side, these probabilities might be different. And then we can also talk about the probability of an event occurring. And this essentially tells us what is the probability that any of the entries in this set occur. So formalized, this means that we take the sum over all values and see what the probability is of a random variable taking that value and summing them all up. So for the case of getting an event where we have even numbers, this would be the sum of x taking on the value 2, 4, or 6. For the case of our fair die, we can say that the probability of getting any number is 1/6. So rolling a 1, rolling a 2, 3, 4, 5, or 6 all have the same probability of 1/6. This does not mean that if we roll the die 6 times, we will definitely get one of each number. That is not what probability means. This probability just means that if we repeat this experiment of rolling a die an infinite amount of times, that 1/6 of the time we will get each number. Now, we can't repeat this experiment an infinite amount of times. But what this means in practice is the more often you repeat the experiment of rolling a die, and the more you count how many times a situation has occurred, divided by the total amount of tries or experiments you've done, that number will keep getting closer to this probability. And then using this probability 1/6 here and inserting it into the sum for our event where we get an even number, we will get the sum 1/6 plus 1/6 plus 1/6, which is 1/2. So 50% of the time, the number showing on the die will be even. Now, one important aspect is that if we sum over the entire sample space the probabilities of these outcomes occurring, this will need to add up to 1. What this essentially means is that the probability of any events in the sample space happening has to be 100%. So this statement always has to be true over our sample space. The consequence of this is that if we want to find out what the probability is of an event not happening, that's what this bar on top of this A is here, where A is a set of outcomes, so an event, that the probability of this occurring is 1 minus the probability of A, so of the event occurring. So A not occurring is the same as 1 minus A occurring. This can be easily verified if you add by the probability of A, because then on the left side we get the probability of A not occurring and the probability of A occurring equals to 1. And this is exactly the sum that we looked at before, since this is all our possibilities. Either event A occurs or doesn't occur. There's no other possibility. Let's consider the case where A and B are events. We can now sketch what they would look like as a Venn diagram. This circle here is our event A, and this one here is our event B. Now there are certain cases where these can overlap, and we have an area here where both A and B have occurred. This does not have to be the case. We can also have it that these are separate. So it's impossible for both of these events to be occurring at the same time. But let's look at the case where they are. We're interested now in the probability of both of these occurring, or either of these occurring. Now you would write this formally as P, A, and then this cup-like symbol, B. And this essentially means or, meaning we want to know what the probability is of A or B occurring. So this can either be an occurrence here, or even here. And interesting here is that both are occurring. So we don't just care if one or the other is occurring, but we're also okay with both of them occurring. We can also ask, when are both of them occurring? And you write this one as A and then this inverse B. And this one can be read like an and. So we only care when A and B are both occurring at the same time. And this will be this area in the middle here. So just A occurring is not enough for us. And so is only B occurring. So only when an occurrence is in the middle here do we care about it. So this entire area here. Now, these were just some of the basics of probabilities. But even just with these, there are certain rules that can be derived that are super powerful, like the addition and multiplication rules for these probabilities, and the bias rule, which is incredibly useful and finds applications, for example, in machine learning. If you enjoyed this video and want to see where probabilities can take us, check out this video where I explain how large language models, like ChatGPT, use probability to create new text. And over here, YouTube is literally using probability right now to suggest you a video it thinks you'll love. Subscribe for more videos like this, and as always, thanks for watching.